Indeed, indeed it is. Okay. So here's what I did. So yesterday, the Monday, Wednesday, Friday section is got started on chapter 2. And unfortunately, what I did, which probably happens actually probably more often than not, is I accidentally saved that under Tuesday, Thursday. So all of the chapter 2 work that I did yesterday with my Monday is kind of labeled Tuesday, Thursday for me. So I'm going to label the PowerPoint I use for you guys Monday, Wednesday, Friday. So I'm going to be a little confused for chapter 2. So if I kind of pull up a PowerPoint, basically is the reason why I'm saying this. If I pull up a PowerPoint, you're looking at it, you're like, that's not where we left off. Then I know I grabbed the wrong one, right? So I can just go back and grab the other one. That happens, unfortunately, a few times a semester, especially when I have 3 of you. And I'm trying to keep you all, like, you're all roughly in the same spots. And I'm trying to remember, okay, wait a minute, you guys left off at slide 6, you guys are slide 5, you guys are slide 7. So that gets messed up pretty easily. Does this look pretty accurate? Closer to the end? Okay, this is what we have. So we were a little.
Yeah, it was. Yeah.
So was it that one right there? So I've actually got notes there.
Well.
And then, so we talked a little bit about models.
Yes.
And then we were getting ready to talk about scientific theory. Is that right? Okay. Okay, cool.
This one, we were on unifying themes in biology.
Okay, because I remember we left off somewhere on unifying themes and then kind of cleaning up. And that's fine. Okay, so let's go ahead and dig in to these unifying themes. So what I want to do is I want to so this last bit, these last kind of chunk of slides that we have is roughly just kind of like the broad overall themes in biology. I'm not going to get into a lot of these, right? So I'm probably going to go directly and start pulling out chapter 2 and label you guys like Monday, Wednesday, Friday, right? So welcome to Monday, Wednesday, Friday. This is where you are now. So these are just, we have entire chapters unpacking these, right? So we'll unpack it there. I just want to sort of highlight some of these things. Obviously, one of the big unifying themes that we have is a cell theory, right? So we have an entire cell chapter that covers cell theory. And we'll talk a lot about that and the structure of cells and how cells are put together and how they work and all that sort of stuff. And so we'll talk a lot about this idea of the cell theory that kind of pulls together all living things. And the reason why it kind of pulls together all living things, especially in biology, right, which is the study of life. The other big major theme that we have actually is DNA, right? And so our molecular concept of how inheritance works. So this is actually probably a more recent concept, a unifying concept in biology. And the reason why it's a unifying concept, right? This is something that pulls all biology together. And the reason why it's a unifying concept is because in order to build a living organism, you have to have the information to do so. And the information comes from DNA. So when you look at DNA, DNA is fundamentally your instructions. It's your blueprint for building you. And around this, so basically just like every building out here, every building that you see everywhere wasn't built just like by the seat of your pants. There is a blueprint for every single structure that we build. There's a plan for it. And in those blueprints is all the information you need in order to build that building. So if I wanted to build Mile High, I could with the blueprints for Mile High. Okay. Now there's a couple of things that I want to take a look at, sort of term things that you run into. So the gene concept, right? So basically a gene, all a gene is there's a modern version of a gene, and then there's kind of more of a 19th century version of a gene. But basically what a gene is a chunk of DNA that encodes information for a particular trait, okay, like hair color, for instance, right? So if you have a specific type of hair color, it's because you have a gene that has the information for that particular color of hair. Okay. And all your traits are like that. The other big term that you've heard me banty around a little bit, but I didn't really explain it, is this concept of a genome, right? So I kind of talked about the sequencing of the human genome. I've talked a little bit about genomics, right, which is the study of the data that you get from sequencing the genome. And but the question is, what is a genome specifically, right? So a genome, there's a couple of different ways you can look at it. So I'm going to take a look at it in two different ways. First of all, I want to take a look and define your genome. Right, so each one of us has our own genome. So what is a genome? A genome is simply the complete set of instructions to build you from scratch. Now, where do you find that genome in you? In the nucleus of every single one of your cells. So in the nucleus of every single one of your cells is all the information that you need to build you from scratch, from zero to where you are now. That's your personal genome. Our personal genome reflects our inheritance. So we've gotten that information from our parents, who got it from their parents, and so forth. So my genome is not the same as yours, right? Because you have different parents and I have different parents. So that's a personal genome. Then you have a bigger sense of the genome, which is the one I've been referring to, and that's the human genome. So the human genome is all of the lump sum information of all 7 billion of our individual genomes piled together, all the information in all the human species, all together. That's the human genome. That's what we sequenced. So we have all that information, okay? And that's the reason why it's powerful, because that's a ton of information. Literally speaking, for the first time in the history of humanity, we have the complete set of instructions, top to bottom, to build a human being from scratch. The problem is we can't make heads or tails of the instructions, right? It's like you know, it's kind of like one of those really bad instructions you get like from like a Christmas present or something like that. And it's like you have to, some assembly required, and you're spending like most of your life there, and you're thinking, wait a minute, what kind of a degree do I need to actually get this put together? It's like, and I need all these tools that I don't have, and it just requires a lot of engineering. And you realize that you've got instructions, but you don't really know how to make sense of them, right? That's kind of where we are now in genomics, which is the reason why genomics is very powerful. Why? Because given time, as long as we don't give up, we will figure out the instructions, and we will be able to learn a lot about how this is put together. And that's the reason why genomics is so powerful.
Technically, women have had their subconscious, like a non-conscious understanding of how to build a human since the very beginning.
Yeah. Yeah, there's a lot of we have a lot of intuitive knowledge that we've never really kind of quantified and formalized, because we're living inside this thing, right? So we get used to it pretty quickly. So the other big theme that we have is the structure function theme, right? So as you kind of go about, and kind of one of the things I always like to sort of to do is like kind of do a little thought experiment, right? So as we kind of go throughout biology, what we want to do is we want to build a biological organism. Right now, what do we need to know in order to build a biological organism? Well, a couple of things. Number one is you kind of need to know why you're building it, right? That's your big biological questions of life. So these are the questions you need to answer. Okay, got it. Okay, so now I know what I'm trying to answer. Now, how do I do that? Right? Doesn't really matter how you do that. As long as you do it, you're good. So there's going to be a lot of variations to this problem, right? There's going to be a lot of different solutions. None of them are going to necessarily be wrong, as long as you get there. Now, what you do know, however, is that in many cases, you're going to have a particular function that you need to achieve in order to answer your big biological question of life. And oftentimes when you have that function, it's like, I need to do this. Then that means you have to come up with some sort of a structure. Here's a good example. I'm going to put a function in front of you, a very simple one. I want you to drive a nail into a piece of wood. How are you going to do that? Okay, a hammer. What does it look like?
The hammer or the process of driving
The hammer itself, right? So you came up with an idea of a tool to solve your function. So how did you build it? What does it look like? What is it composed of? What was the handle made of? What was the head made of? Why? Why not make the head out of marshmallow? Because there's a function you're trying to do, right? A marshmallow will not hammer a nail, right? Why not make the entire thing out of that? You said the handle was wood, right? Or plastic. Or plastic. So why not have the handle made out of?
You gotta have some, if you hold it on your finger, that's to be like heavier on one side, so you can't feel the same way.
So kind of the fulcrum thing, right? So you're basically having more dense substance on one side.
You get more swing to it.
So you got a little bit of a leverage thing going on. So you're using your physics, right, to solve this problem. But why wood or plastic? Cheaper. It's solid, right? I mean, if you had, say, for instance, a metal hammer with a metal handle.
It's heavy.
Yeah, right. It's gonna do you. So the thing you're going for is going to be all out of whack, right? Because you've got an imbalance because you got heavy on one end and heavy on the other. It's going to be difficult to get that leverage thing, right? So now what's happening is you're building structure to solve your problem. Oh, by the way, you came up with a hammer. Why? Because we've already invented it. But we haven't invented anything to drive this nail. Remember, it's a clean slate. Are there any other options to drive this nail? A rock? Would that do the job? Sure. Would sandstone be a good choice?
No.
No. How about granite? Marble? Yeah, would that work? Is that different than a hammer? Even within the hammer family, are there different types of hammers? If you have a lot of nailing to do, are you going to be using the traditional hammerhead hammer? What do you usually have? A nail gun, right? With the air compressor on there. Is that basically a hammer? Yeah. So you can see that you have a spectrum of different things. Here's a good example. What if the nail or the thing that I'm hammering is not metal? What if it's like a little wooden dowel? Would you be using the metal-headed hammer? Woodworkers? Yeah, a wood mallet, right? Is that basically a hammer? Is it constructed the same?
No.
Really?
No.
What is it made out of? Yeah, the head is what? Rubber, right? You said rubber, right? Right, so it is not the same, is it? What's going to happen if you get that wooden dowel with a carpenter's hammer? You'll destroy the wood, right? Notice what's happening. Subtle shifts in function. Basic function. You're driving something in, right? Subtle shift in function requires you to redraw the structure. So when you take a look at a family of hammers, carpenter's hammer, woodworker's hammer, the rubber mallet, the air gun, they all have a similar function. They're driving something. But the structure is different. Why? Because what you're trying to achieve is like, you're still in the hammer family, but your functions are very specific to the structure. Now, would you drive a metal nail with a rubber mallet? Now, it is a hammer, yes, but it's not structurally created to hammer the metal nail. Notice the relationship between my changing functions and my required changing structure. We see that all the way throughout biology. Oftentimes, we don't understand the function. Now, in carpentry and in construction, we have the function in our head first. And then we kind of scramble around saying like, okay, what do I need to do this? This is what I want to do. I know what I want to do, but I what tool do I need to do this, right? So it's kind of like a little bit on the backside, but when we study this, we see as students, is we see the structure coming at us, and we don't understand the function as well. The function comes a little bit later, right? And so that's kind of where we kind of get into this sort of, then when we get deep into the woods, we're like, wait a minute, I'm studying all this structure, but like, why, right? Why is this here? And usually when you're in that zone, it's because you see a structure, you see the mallet. I mean, if you don't know anything about what's going on, you see this rubber mallet, you're like, yeah, I can look at this, study this rubber mallet, I can study its construction, what type of wood it's made out of, you know, the density of the rubber, the hardness of the rubber that it's made out of. I can really characterize this rubber mallet and understand it very well. But then I can step back and say, like, yeah, I still don't really know why this is rubber and not metal, right? So that's because that's a functional thing. And so oftentimes we kind of get into that, and the idea is we have to sort of research that, sort of study it, and to be able to figure out why this is rubber. That's the relationship between structure and function. This is an enormous relationship. Basically speaking, it goes like this. To build structure, to build a hammer, is incredibly expensive. And guess what you don't have a lot of? Yeah. As a student, probably that's reality, right? But also as a cell. As a cell, you don't have a lot of cellular money. You don't have a lot of energy. So you have to budget and budget wisely. So there is no such thing as discretionary income. Most of us in the 21st century have some sort of an entertainment budget. Whether we know it or not, we do. Why? Because you spend stuff on things that you don't need. Like the games on your phone, right? The purchases that you make that are fun, right? Those fun purchases. Those are all discretionary purposes. If you don't need it for survival, guess what? It's discretionary. So even in our most desperate, and this is kind of funny in the West, right? I mean, even like when we are just burned out and on the street with a cardboard sign, guess what? We're whipping out of our pocket our nice cell phone, right? Which is always kind of a little hysterical to me, because every now and then I'll see somebody, you know, with a cardboard sign, and they'll pull out a phone that's like better than mine. I'm like, you realize your phone is actually more expensive than mine. So you actually have better equipment than I have. I can't afford that. Apparently the cardboard approach is a lucrative deal. I got to look into that one. Some side income perhaps. Might be able to buy my Bentley after all, instead of my 15-year-old Ford Escape.
Go back to the hammer metaphor. Would it be like, you wouldn't buy one of every type of hammer, you would buy the hammer you need to get the job done?
Exactly. Exactly. So if you're a woodworker, you don't need the carpenter's hammer, right? You need the rubber mallet because that's what you're working. If you're a carpenter, then you're going to be needing the carpenter's hammer, right? You're not going to be needing the wood mallet. So if you bought the wood mallet, that would be considered a discretionary purchase. You're not hammering wooden dowels right now. So the purchase you just made is a waste of money. Oh yeah. Yeah. Matter of fact, I mean, energy is very precious. That's the reason why we are very desperate for it. And why we eat each other. Because energy is very, very limiting, right? But that's basically going to dictate what kind of structure you can build. And that's going to dictate what you can do. Okay. By the way, if I need a rubber mallet in order to achieve my function, and I don't have the energetic capacity to get that rubber mallet, guess what? I don't do that function. It's as simple as that. I have to figure out some other way. I got to figure out something else that I can get a hold of. Okay. So basically, that's an important thing, right? That structure function component is an important thing. The other big thing is information, right? Because DNA is an informational molecule, then all this information, all this structure building, by the way, that the cell does, that's really, really expensive, is basically all informed by DNA. So you don't really have the capacity to build structure until you actually have the plan and the information in order to build that structure. So if I don't have the plans or the idea to build a rubber mallet, then it just doesn't exist. That's the flow of information, right? Every building, like I said, doesn't build itself. You have to have the plan to build it first, and then you build the structure. That further constrains the structure function linkage, right? It's great if you've got the function or you need the function, but if you don't have the basic blueprint to build the structure you need to satisfy that function, you're out of luck, right? So that kind of constrains what you have. The other big unifying idea that we have in biology is equilibrium, right? This actually comes from chemistry. But in equilibrium, basically what equilibrium is, if you're not aware of it in chemistry, is basically equilibrium is when a chemical reaction comes into a sense of balance. That is to say, the rate of the reaction going forward is in balance, not equal to, but in balance with the rate of the reaction going backwards. So there's kind of like the sense of balance where everything kind of chemically is like a placid pond, right? A pond that is glass still is equilibrium. Now, in biology, equilibrium is boring. And none of that, but we don't get anything good out of equilibrium. What we want out of equilibrium is disturbance. So in biology, what we do is we throw a rock in that pond, and that disturbs the equilibrium and causes ripples. Now, biological ripples or deviations from equilibrium usually have some sort of biological benefit for us. And so we intentionally disturb equilibrium so that we can actually get biological benefit. That's what we have to do. But the idea is universally, all systems, for the most part, always achieve to go back to equilibrium, right? That's kind of like your set point. So unless I do anything, all these systems, including us, which we're an open system in the universe, we all try to get back to equilibrium. Now, in order to keep you out of equilibrium so we can do something interesting, I have to keep messing with you. I have to keep throwing rocks in the pond. Otherwise, it will eventually go back to equilibrium. And that's true in biology. We don't really get any biological function out of a nice, placid biological pond. Mhm. Okay, so that is the end of one. Any questions on one? Let's see how many times CCD is going to make me log in here. Of course it did. No, want AMP. Hey, there it is. Let's just take it. Let's see if we can grab it. There. Maybe I will recognize that now as your guys' Tuesday, Thursday real chapter 2. Okay. Keeping all these windows open benefited after all. Okay. Let's go ahead and dig in to the chemistry chapter, right? So the chapter 2, the next chapter we have, now we kind of laid down some groundwork, we laid some of the basic principles. Now we kind of roll up our sleeves and kind of get to the nitty gritty, the process of actually starting to build out this biological organism. Now, the one thing to always understand is that we always have to start with the foundation. And the foundation of life is built on chemistry. Now, the foundation of chemistry is built on physics, right? So these ideas all form the stable ground upon which we can build our organism. So before we start actually looking to build our organism, we have to take a look at foundation building, okay? So physics governs the activities of the universe. Everybody, chemistry, biology, you name it, all of them are beholden to the laws of physics, right? So they're all governed by the laws of physics. So chemistry is built on the laws of physics, and then chemistry will inform and be the foundation upon which living organisms are built. So the foundation of life is built on a combination, a layered foundation. The immediate brickwork, if you will, of biology is built on top of chemistry. And underneath, supporting chemistry, is physics. Living organisms have to adhere to both sets of rules, both chemical law and physical law, right? We cannot violate it. So let's start laying down, and the physics law, by the way, there's not a physics of life, like there's not a biophysics chapter. That would be painful. You probably would not like that chapter, actually. So the laws of physics that weave and set the parameters and the stage for the rules by which life, the things that it can and cannot do, right? What is out of bounds and what is in bounds. When those physical laws come into play, what I do is I just weave them into the discussion, and I'll kind of set those up so you can see in context of the biological discussion how the laws of physics are setting the boundaries and the parameters for that discussion, that activity. Make sense? Okay, so let's start off then with chemistry. So chemistry So in chemistry, basically, we want to start off with the idea of matter, right? And so matter is essentially anything that has mass, right? So if you take up space or have volume, then you're matter. And we learned when we looked at the levels of organization that the lowest level of organization is the level of the atom, right? And the atom is something that we are all composed of, both living and non-living, right? So you are composed of atoms, the snow is composed of atoms, this is composed of atoms, everything that is stuff, that is physical matter in the universe, not just on the earth, but in the entire universe, is composed of atoms. Now, there's a couple of ways to describe matter. And I'm going to put the triple dot there to define, to tell you that's a definition. And one is a definition of atoms. The other one is what's referred to as the element. And I wanted to find both, but I wanted to find element first because we kind of talked a little bit about atoms already. And I want to kind of fill that out a bit. But now what I want to do is I want to focus in on the idea of the element, and I want to define what we mean by the element. So an element is any substance that cannot be broken down into any other substance. It's pure. Okay. Now that is one type of a descriptor of element. And actually we'll talk about, technically speaking on the slides, we'll have element, but it comes a few slides down. I tend to like to define element and atom at the same time to kind of foil them against each other so you can kind of see what some of their differences are. Now that's great, right? So any substance that cannot be broken down into any other substance. So it's pure, it's complete, it's homogeneous, right? Okay, so what does that mean about the atom, right? So how do we define the atom? The atom basically we refer to as the basic unit of matter. Does that sound familiar? we had a similar phrase for the cell, didn't we, in the last chapter? We said that the cell was the basic unit of life, and I had to sort of break that down and explain to you what that meant when we say the basic unit of life. Well, the same thing's true here, right? So this is the basic unit of matter. So the question is, what do we mean by that exactly? So what we mean by that is this, that this is the smallest that we can get and still retain the properties of the element. Okay, so here's what I want to do to kind of illustrate the difference between element and atom. Okay, so I'm going to draw here like a little gold ingot, right, with a little mint stamp on it, right? So this isn't like your electroplated gold. This is the real deal, right? So it's like a little gold bar, and it's pure gold. Gold is one of the naturally occurring elements in nature. There's like about 90, 92 of them. And if you're wondering what I keep looking around for, that I'm very disappointed is not anywhere to be found, which I guess is to be expected in a microbiology lab, is a periodic table. But I don't, I mean, they're nice to refer to because I can actually point stuff out, but I can see if chemistry might have something. Yeah, that's, well, and it's kind of because in general bio, we talk a little bit more about this stuff, and micro, they don't really talk about chemicals a whole lot. So I'll see if chemistry has like a little, like a flip chart or something like that, just something you can just refer to while we're doing this. Because I mean, I can find one, but I'd have to pull off the slides and pull something up, so it would be a little more cumbersome. Here's what I want to do. Anybody know what the elemental symbol of gold is? AU, you're right. So here's what I want to do. So it's an element, right? So it's one of the naturally occurring elements, of which there's like 90, 92 of them. A lot of the other ones after that are just, they're manufactured, right? Thanks to CERN and things like that. Is that a question or a stretch? Or both? As natural? Yeah. No, because usually, well, it depends. If you're a chemistry person, you don't make as big a deal about it. But when you're a biology person, what you're doing, because you're not just trying to create elements for kicks. That's what chemistry people are doing, and particle physics people are doing. So like all those things that they're making in the super colliders are interesting from a particle physics standpoint, from a chemistry standpoint, but they're completely useless from a biological standpoint, because what we're focused on is, I don't really care about all the stuff we can create in a lab, because that's not what we have when we're building an organism. All we have when we're building an organism are the stable elements that are to be found in nature and that can be relied upon. So I got a couple of questions.
I was just gonna say that the man-made elements are super, super unstable and don't last very long. So it's more of a doing it because we can than a doing it because it'll have a practical application.
Yeah, it's more of a parlor trick. So it's like milliseconds, literally, is how long they're around. So that's the reason why we don't, in biology, it's not really, we don't really care about those. So.
What's the super collider do?
Yeah, so the super collider, so what it basically does is it takes particles that we have, and then it accelerates them through this like long kind of like racetrack, and it got like magnetic fields and kind of helps to propel them and things like that. So you got these like subatomic particles like whizzing through this racetrack, and then what they do, they literally just collide them into each other like a car wreck. It's like wrecking two cars into each other, and then you kind of sift through the debris to figure out, you know, what that looks like. So it's kind of like, if you think of like an atom is kind of like a car that you can't pop the hood on. So you're not quite sure what's inside. You know, whatever it is working, So the only way you have to figure out what's inside is to blow the thing up and then take a look at the wreckage. Right? That's kind of the way, that's what a super collider does. Chris, was that another question back there? Yeah. Yeah, it's in CERN in Switzerland. Yeah, that's what I'm talking about. So yeah, when I say CERN, that's this facility where we are able to do crazy stuff. It's actually kind of concerning because literally we're dealing with stuff that's like, I mean, we can really like annihilate the fabric of the universe with the kind of stuff they're playing around with. It's actually, it's fascinating and frightening at the same time. It's kind of like giving like a toddler a loaded gun. Right, that's kind of what it's like a little bit. So we're not developed nearly enough to be able to handle that kind of responsibility. So yeah, we're going to kill ourselves. That's just how it's all going to end, you know. So okay, so let's go ahead and do this kind of little example here. So let's take a look at our gold bar. Now here's the deal. I'm going to cut this gold bar in half. Is that top half still gold? Sure it is. I'm going to cut this in half again. Is that top half still gold? Sure, good. Cut it in half like this. Is that little corner still gold? So let's keep going. Is that top rectangle still gold? Yep. Is that little square still gold? Sure. If I take a little smidge of this, here's my smidge. Is that smidge still gold? Sure. Now, if I break this down to a single atom, is that atom still gold? Ooh, a little bit of, right, a little uncertainty. The uncertainty principle is starting to set in.
As long as you're not doing anything to protons, it's still gold.
Yeah, right, because that's our definition, right? So the definition is the atom level is the smallest you can get and still retain all the properties of gold. Right? What are those properties, by the way? Why do we love gold so much? Luster. So, yep.
It's sorry, chemically speaking. Not
Yeah.
it.
So what are some other, just describe it to me. Imagine I've never seen gold before in my life and I'm blind. So I don't know what it looks like. You have to describe it to me. You're holding like a gold bar in your hand. Describe it to me. It's shiny, right? That's one. Okay. Heavy. So it's got density to it. Okay. Keep going. It's yellow. It's color. It's got a very distinct yellow color, right? So much so that we actually call it gold. It's got its own color spectrum. But so that's a little bit different. So natural gold is yellow. So when we actually get into metallurgy, we kind of dork around with metals a lot. And we kind of corrupt them. We can create different alloys and different sorts of things. We can technically call it's like, oh, well, this is white gold, but we kind of have different metallurgical processes that kind of mess up the original natural substance. So I'm thinking always on the natural level. So what we actually find in nature. So it's soft, right? What else? Which, by the way, is a physical property that's related to the more technical version of that, which is malleability, right? Which means you can hammer it out, you can distort it easily, so it's very malleable.
Blind, when you said yellow, you probably wouldn't know what you're talking about.
Well, that's true, but at least you would be able to describe it to me that it's yellow. What else? There's a harder one that you probably don't think about, actually. Electronics.
Oh, yeah, conductive.
It's very conductive, right? It's actually the best conductor. As a matter of fact, if you want the best, most efficient system, you make your parts out of gold, not out of copper. And as a matter of fact, if I don't know if any of you guys have been down to the Space Museum down in Colorado Springs, which is really cool. But in some of, if you pay close attention, in some of the stuff they display, which they have a bunch of stuff that's kind of cool, that's all been in space and it's been retired, and they just kind of stick it in there, right? But they've got some things in there. If you take a look at it, where you can actually see some of the circuitry is gold. Like of some of the things that they're shooting out there, some of their circuitry is gold because they need like the absolute best efficient conductor out there. So that's the reason why the space program is so expensive. But yeah, so all of those attributes and all of those traits are all encoded in the structure of the atom. Now, let's go ahead and go one step further. Let's blow this atom up. Once I blow that atom up, is it still gold? No. Why? Because now we are smaller than the atomic level. What did we say? The atom is the smallest you can get and still retain those properties. If you get smaller than that, you've lost it. Okay. Another kind of a quick analogy is you guys. All of you guys right here are 1111 students, yes? Okay, let's cut you in now. I'm gonna go over here. I'm gonna take on my agent. Right. So all of you guys now in this half of the room, you're 1111 students still, right? Okay, let's go ahead and cut you guys out. I'm gonna just focus on you guys right now. You four are 1111 students, yes? Okay. Let me cut you guys right here. You two are 1111 students, yes? I'm gonna cut you guys right in the middle. You're still an 1111 student, yes? With all of the properties of an 1111 student. Yes? So you retain all those properties. Now, let's go one step further. I'm going to rip off your arms and your legs and then cut your head off. Are you still an 1111 student? Really? If I cut your head off, your arms off, and your legs? No, right? What are you now? Body parts, right? So what does that mean? That means that where you are right now is the smallest you can get and still retain all the properties of an 1111 student. If I were to blow you up, you're just body parts, right? If you were to blow the atom up, it's atomic body parts. Okay. So that's kind of a similar sort of way. Now let's take a look at these body parts, shall we? So in a nucleus, an atom, you have a couple of different areas of the atom that's typical for all atoms. So generally speaking, in the center of the atom, you have the nucleus, and then surrounding that nucleus is going to be your electron cloud. We're going to take a look at what's in here in terms of some of these subatomic particles. In the nucleus itself, we have two different particles that are large. So the proton, which is large in mass, it has a large mass. It's also positively charged, these protons are. And we typically will abbreviate it as P+. That's basically abbreviation for the protons. This is all in the nucleus. So let's go ahead and I'm going to add a couple of protons here. So let's do that. So put a positive charge in there. So there it is. I've got 3 protons. Now also in the nucleus is going to be another large particle, the neutron. This is also going to be a large by mass particle. It's going to be neutral. That is to say, it has no charge at all. And we typically abbreviate this as N0. This is also going to be residing in the nucleus as well. So I'm going to draw a couple of neutrons in here. Let's do this. I'm going to put a slash through them to indicate no charge. Okay. So there's our little nucleus. We got 2 different types of very large, massively large particles in the proton and the neutron. Now then, the last particle that we have is the electrons. Now the electrons are negatively charged particles that by size are vanishingly small. And they are typically abbreviated E negative. So they're negatively charged particles. And these guys are to be found whizzing around the nucleus in structures or in pathways, if you will, called orbitals. Okay. Now, one thing I want to kind of tease out, because this term right here, vanishingly small, is actually a term that my Chem 101 instructor used, and just kind of for kicks. And he was kind of a very practical guy, so I kind of felt like saying using the adverb kind of descriptor, vanishingly small. Like, why didn't just say really small? Yeah, really tiny. I asked him, well, why did you say like vanishing? And the way he said it was like very theatrical. It's like vanishingly small. I mean, he was like, wow. So So I was like, okay, so what, are you just like hyperbolizing? You're just trying to make the point, right? Is it like a little bit of performance art? Is that what's going on here? Or is there something more? And he was like, no. That word is intentional, he said. And it is a very accurate descriptor of an electron. Here's the reason why. The reason why he selected vanishingly and not just say very small. What do you think of if I say something is vanishingly?
It's getting smaller.
Gone, getting smaller. Basically, you have something that's so small, it's almost as if it's like literally, almost like at risk of just winking out of existence. Like literally just disappearing out of existence. It's so tiny. And that's why he said vanishingly. He said, imagine that the electrons are so tiny that they're literally just right there on the precipice, like dangling on the edge of the cliff of existence. They're so tiny. They're literally at risk of just falling out of non-existence. They're so small. Yeah. Well, it's not actually vanishing in process. It's just really tiny. So it's actually stable. So it's not like it's imploding or disappearing or fading to black or anything like that. It's there, it's stable, but it's just really, really tiny. It's just so small. It's almost as if it's, from our perspective, it's almost as if it's kind of on the precipice of disappearing altogether. Okay. Exactly, right? So those electrons will be out here. So I've got 3 of them out here. And these guys will be zipping around in their orbitals and then basically kind of happily moving around the nucleus. Look familiar? It's your basic, right, logo for an atom. And that's your cloud. So you're hanging out in the cloud. So let's go ahead and take a look at some examples of this. There's 2 different models here that we have. One more accurate than the other, one more intentional than the other. But basically what we have here is 2 different atoms. So we have a hydrogen, which has 1 proton and 1 electron. And so you can see this proton is going to be in the middle of the nucleus. And then this yellow fog bank out here, this is basically a statistical area where the electrons reside. So what I mean by statistical area is this is basically the neighborhood, if you will, the orbital, right, of where the electron can be found at any given point in time. But because the electrons are moving so quickly, it's not like they're inhabiting a discrete space. So they can randomly appear anywhere in this yellow fog. So it is a statistical representation. So for instance, if this 1 electron is zipping around inside this electron cloud, this yellow haze, if you will, then if I stop time, then that electron will be found somewhere in that yellow fog. If I start it up again, it's going to be zipping around, and I stop it again, it'll be somewhere else in the yellow fog. If I let it go again, it'll be zipping around, and it'll stop it, and it'll be somewhere else. But it'll always be in that yellow electron cloud. Okay. So that's one example. A larger example of that is oxygen. So oxygen has 8 protons and 8 neutrons. So you can see you've got your neutrons here in blue, your protons in white. So you can see you've got a more substantial nucleus, but you still have your 8 electrons in the cloud, right? But now guess what? You've got more electrons, which means you need more neighborhoods. You need more orbitals in order to sort of situate them. So within the context of the cloud, you have individual neighborhoods, just like you have Metro Denver has all the Denverites in it, but we don't all live in the same place, do we? We all kind of are cordoned off into our neighborhoods. And so different folks will basically reside in their neighborhoods. And the idea of a neighborhood is this is where you live and shop and do whatever you do, right? So most of your living is done within the context of that neighborhood. Right? That's kind of the original idea of the neighborhood. That's kind of where you did life. So you didn't really have a whole lot of contact with other neighborhoods, perhaps, at least back in the day. Now we're rangy, right? So we sleep in one neighborhood, we do other things in other neighborhoods. And so we're all over the place now. So it's a little different now, but originally that's what the neighborhood idea was. But this is where you lived within the greater context of this sort of Denver population cloud. Bella.
Does hydrogen not have a neutron?
No. Nope, it is the simplest atom that we can get. So we'll talk a little bit more about those neighborhoods. By the way, those neighborhoods that these electrons live in are the orbitals. So within the cloud, you have specific orbitals. And just like neighborhoods have a very distinct personality, orbitals also have a very distinct personality. So that's something we'll talk about here in just a second. So this type of model, this will basically represent an accurate spatial organization of the electron. So this basically, if you want to know where this electron is in any given point in time, that's this model. Okay. Now, this is kind of how it looks now. This is how we think of it now. But back in the day, before we understood how this worked, the spatial orientation of all of this, we had this. And what this is what's referred to as the Bohr model. Now, Dr. Dillman, one of our chemistry professors, is probably screeching right now for some unknown reason. Because from our chemistry knowledge and the way we understand quantum mechanics and things like that and how these sorts of things works, what we know for sure is that the Bohr model is not correct. And so the fact that we have the Bohr model in biology and we actually use the Bohr model is kind of like nails on a chalkboard to a chemistry purist. Okay. Which is the reason why I always mention Dr. Dillman, because he's a great guy. If you take chemistry, take him, students love him. But yeah, he would say like, well, this is not even accurate. Well, yeah, I know. But the thing is, we're not chemistry. In biology, we use this for a different reason than we do in chemistry. Right? In chemistry, you're trying to understand how things actually work. This is the reason why you go to this one. This is our most accurate model right now. And this is the reason why you do away with this one, because now we know this one doesn't work, right? That's what chemistry is after. But that's not our point in biology. Our point in biology is we use this one not for the purpose or the intention of saying this is the way it is, because we know it's not this way. The reason why we use the Bohr model is to diagram out the electrons. So this is basically a diagrammatic representation of electron personality. It's not real. It's just an organizational tool for us. We use it as an organizational tool to help us simplify our understanding of how electrons are related to each other, because not all electrons are the same. Christopher, was that a question going up or? Well, no, because actually what the Bohr model did, because actually Niels Bohr is the one who came up with this, who's actually a Nobel laureate. So he actually got the Nobel Prize in chemistry. So he's not a dummy. He's a pretty smart guy. But the thing is, we came up with this one in like, oh gosh, 1920s, something like that. It's early, right? So we didn't know a lot about quantum mechanics at all. So that was later on. So this was like our first idea from what we knew and what we thought originally. And the reason why the Bohr model is wrong is we actually thought that what happened, the way it worked, was that the nucleus was in the middle, very much like the sun is in the center of the solar system. And the planets, or in this case, the electrons, orbited that sun in a definable, calculable trajectory, right? So it was like a galactic orbit. And the way we originally thought was that the electrons moved around the protons, or the nucleus in this case, in a very definable kind of an orbit, very similar to the way planets have a definable, calculable orbit around the sun. So what we found out was that that's not the case, because even though, and then this is the nice thing, right? So if you're kind of take your astronomy 101, the nice thing about the orbits, the galactic orbits, the planetary orbits, is that they are very, how should we say, they're very discrete, right? So like, for instance, because they are essentially a curved version of straight line velocity, we actually have calculations that will help us predict where any given planet will be in its orbit at any given time. So if I wanted to know where Jupiter is going to be in its orbit, in 6 months, I can do that because the trajectory of the orbit is completely calculable in math. That's like astronomy 101, right? So you can calculate everything about that arc. It's very discrete. But the problem is when you go and try to calculate the orbit of an electron, it is not discrete. Why? Because it is not discretely moving around in a calculatable orbit the way the planets are. It is randomly ping-ponging around, right? Just like in the context of this cloud. So where it ends up at a given point is random. So once I speed this guy up, so let's say I stop him right here. If I try to predict where's this guy going to go next when I start this up, you don't know because it is a random, it's like shooting around randomly. So you can't calculate random, right? You can only calculate non-random. And that was our first hint that the Bohr model is breaking down. Now we don't think of it as a galactic solar system of electrons anymore. We simply use the Bohr model to help us organize our electrons into families of related electrons. That makes sense? So it's a schematic for us to sort of help us understand and categorize and organize the different types of electrons. And more importantly, what those consequences of those different electrons' personalities are on chemistry. Question?
But then how do valence electrons work?
So for the first one, so your personality as an electron, like for instance, a valence electron has a very distinct personality to it. All these electrons retain their personalities, right? Because the personality of the electron is something that's intrinsic to the electron. What you're seeing in the first one is simply its spatial orientation. So when we say outermost shell, that's actually kind of a bit of a, how should we say, a misnomeric holdover from the Bohr model days. In reality, there is no outermost anything. This is just an inherent personality of the valence. So the valence electrons, technically speaking, never were outer anything, ever. Right? But we hang on to that terminology because it helps us to understand them better. That's the only reason why we do that. So that's an example of language that is a holdover from the Bohr model. That's not accurate. So what that means is these so-called outermost electrons can basically in any given time be right next to an innermost electron in space, right? There's not like she's not on the lower ring and I'm on the outer ring spatially. We can be whizzing around, we can be right next to each other at any given point. And then we just kind of zip around and do our thing. Does that make sense? Okay. Is there another question? Within the cloud itself? Yeah, there's a certain number of orbitals and there's certain types of orbitals. And those kind of represent the neighborhoods within which the electrons will live. And we're going to talk about the orbitals. Yeah, because right now we just sort of laid it out there, but we're going to dig in a little bit more and kind of flesh that out a bit more. So hopefully once we get to that orbital page, that'll make the orbitals make more sense. Hopefully, if it doesn't, follow up on it, right? So keep after me. So for the Bohr model, then you can see basically you kind of keep arranging these are electrons around the nucleus in sort of these galactic orbits. And these little galactic orbits have kind of like definitional parameters associated with them in terms of how you actually arrange those electrons out there. And we're going to do that here in probably in this chapter. So you'll kind of see that. We'll kind of play around with that a little bit. But remember, that's not reality. That's just schematic, right? That's just us trying to categorize the different personalities of electrons so we can understand their behavior better. That's all we're after. We just want to understand their behavior a little bit better. So that kind of gets us to atomic number. And by the way, one thing I want to do here at this point, and I always do this at this point for every class, is I'm going to drop a little bit of slide in here. And this basically represents one of those moments where this would normally be like a whiteboard moment if I weren't taking notes on the computer screen. So I do it here so that it can get recorded on the Zoom and it can be part of the overall file that you guys are able to go back to. So what I want to do is I want to stop here and pause and kind of pull some things together on one side. That's usually what these slides are. Is there's a bunch of different disparate pieces, and I want to kind of pull them all into one place so that it makes a little bit more sense for you guys. But this one in particular is a little bit different in the sense that I'm pulling some stuff together, but it's also something that you don't really see in a lot of textbooks. And what I want to do is I want to clarify some things before we go too far into chemistry, just to make sure that everybody understands very clearly notationally the sorts of things and their meanings that you'll see as we start to move forward in chemistry. And essentially, I want to talk about the elemental symbols and information around them. That's a long title. That's longer than I want it to be. There it is. Okay. So what I want to do is I want to, here's my generic elemental symbol. There is no X, by the way. That's just generic. But what I want to do is I want to basically, whenever you see an elemental symbol, there are different locations on this elemental symbol where we will write numbers and information. And a lot of times in chemistry, what we do is we start writing stuff in these areas, and we just kind of we just go. We just go with it. We start drawing out chemical reactions, and we just sort of hope you're along for the ride. And sometimes you are, and sometimes you're not. I remember taking Chem 101. I mean, this was a situation where they were writing chemical reactions, and I mean, everything was going, and it was like, and I was just like, I was still like, okay, I'm trying to follow along the chemical reaction, but then at the same time, I'm like, okay, wait a minute, what does that mean again? And so like half of my brain was trying to figure out like, what does that mean when he puts a number there, right? And I'm still trying to figure that one out. And then he's just kind of like going on with chemical reactions. So it was difficult for me to try to keep track of both, because it went for like at least a good 2 or 3 weeks into the semester. And I'm like, okay, now I'm just now realizing what you mean when you write a number there, right? But that's a lot of like, okay, I could have done a lot better if I'd known this ahead of time, right? And so that's what I want to do. I want to basically sort of decode the types of information that we can actually put around an elemental symbol, what we mean by that. The first position, number 1, what we put here typically is the atomic number. What is the atomic number? It's your number of protons. That's what it is. Okay. And it's also equal to your atomic ID. This is who you are. And I want to give you an example here. Typically speaking, on the periodic table, you'll find the atomic number usually above the elemental symbol somewhere. Sometimes it'll be like dead center above, sometimes it'll be shifted in the right top upper corner. Sometimes, but rarely, it's in the upper left corner. It's usually not there, but it's usually either directly above or in the upper right corner. I'm going to start off with this one. What is this? Carbon, right? And how many protons does carbon have? Ooh, you don't have this one tattooed on you somewhere? You will after the semester. So how many protons do we have here? No reason for you to know this, by the way, off the top of your head. So yeah, it has 6, right? So do you have a periodic table up there, Heaven? Or you just, okay. Good guess, by the way. Go play the lottery. If that is a good guess, that means you're on a roll, right? So basically you have 6 protons, right? And that 6 protons defines you as carbon. So here's the thing. What if I were to change the number of protons? What if I were to add a proton to it? I would have what? 7 protons, yes? Anybody know what I would be then? Would I still be carbon?
No, you're nitrogen.
I'm nitrogen now, right? Notice what I did. If you change the number of protons, you change your ID. If I take a proton away, I'm now 5. What am I now?
Oh, you are boron.
You're boron. Are you carbon? No. So you cannot change your number of protons without changing your identity, right? It's just like any kind of an ID number you may have, right? A social security number or your S number. If you were to change your S number by like 1 digit, does CCD recognize who you are anymore? No, it sees you as somebody else, right? Same thing's true for the atomic ID, the atomic number. That's your identity. Now, in general, and generally speaking, most atoms do not want to change their identity. The only time they're willing to change their identity is if they are incredibly unstable. In which case, becoming a more stable something else is more preferable than being an unstable you, right? But those are rare cases. And when that happens, usually that is a radioactive element. Okay. Generally speaking, you do not want to change your identity. Okay, position number 2. What is position number 2? Atomic mass. And atomic mass is equal to the number of protons plus the number of neutrons. Why not electrons?
Initially small.
Yeah, they're not even existent, right? They have, I mean, they're so small relative to the protons and neutrons that you don't even count them, right? It's like if I had you get a watermelon out of the watermelon patch and I said, weigh the watermelon, tell me how much it is. I mean, would you make an accounting for like, oh, well, this is the weight of the watermelon, but then when I cleaned up all the dust off of it, it was this. I mean, are you accounting for all the dust that's on the rind? Why?
Because it doesn't add much.
It's negligible, right? I mean, the dust that's on the watermelon is so minuscule in size that it doesn't affect the mass. So your mass is your atomic mass is protons plus neutrons. That's in position 2. So some, like for instance, carbon has carbon 12, which basically means what? How many protons does it have?
No, it's 6.
Protons, 6, right? So how many neutrons does it have? Right? So 6 plus 6 equals. See, 3rd grade math comes in handy. You're like, go for 3rd grade, right? Okay, but there are other types of carbon. There's carbon 12. There's also carbon 13. Notice I write the number up in the position 2. There's also carbon 14, right? Those are mass numbers. Oftentimes you also see this written out. So for instance, you may see something like this, carbon 14. So when you see it written out like that, that is a mass number they're talking about, okay? Generally speaking, you only see information in this if you're dealing with like radioactive isotopes, nuclear chemistry, things like that, right? Where you have different types of mass. You have carbons of different mass, or uraniums of different mass, or plutoniums of different mass. That's usually what you're talking about. You're usually talking about nuclear stuff, okay? So that's position number 2. Position number 3, this is going to be your charge on an ion. So what does that mean? That means your number of protons is not equal to your number of electrons. Okay, so here's the thing. A periodic table, this periodic table, which Belle actually has in front of her, it's very colorful, by the way, right? So everything that you see on the periodic table, the naturally occurring ones, right? That's the first 90, 92 or so, depending on which source you're looking at. Those, as they're presented on the periodic table, are always naturally occurring, are neutral. That is to say that they have the same number of positive charge and negative charge. So if carbon on the periodic table has how many protons? How many electrons does it have? 6, right? However, in cases where your protons are not equal to your electrons, that will not be true, right? That is an ion. And typically you have to do something in order to create that ion. So it's not like a naturally occurring sort of a thing. So ions, the elements in nature, at least on the periodic table, are neutral in nature. So what does that mean? That means you can get different types of charges. The charges you can get will come in either a -3, -2, -1. You could have a 0 charge on there, or a +1, +2, and a +3. You usually don't get +4. That just gets too big. Okay. Now, if you're on the negative side, what this basically means is the number of electrons you have is greater than the number of protons. The positive side, the number of electrons you have is less than the number of protons. Let's start with the positive charge, shall we? How do you get a positive charge from your electrons and your protons? What are you going to do? Lose an electron. Anybody tempted to add a proton? It makes sense, right? That's kind of the way our brain works. Our brain works additively. It's like, oh, if I want positive charge, I need to add an extra positive charge, right? What would happen though? Let's just follow that, right? What would happen though if you added a proton? You're no longer who you were, right? So sticking with the original thing, I do not want to be something else. Then do you want to add a proton? Do you ever want to take a proton away? So then how do you get ions then? By either taking the electrons away, which if you take the electron away, you're going to get what? A positive ion, right? If you add electrons, you're going to get negative. So the protons in the nucleus in general are generally tightly held by an atom. The larger the atom gets, the more electrons you get out there, the more you're able to kind of swap them around a little bit. So you'll pick some up, you'll give some away, and you're just kind of like, you know, it's like currency. It's like, here, I got some electrons, I can do away with some of them. That makes me a little happier, you know. So you kind of like are swapping them around. Okay. So a good example of that would be sodium, which typically picks up a +1 charge. Magnesium, which is a +2. Oxygen, which picks up a -2. Right. So these are different types of ions that you would see. Now in position 4, this is basically going to be the number of atoms in a molecule. So here's a good molecule here, C6H12O6. Anybody know what that is? There's no reason why, you know, it's not like, you don't know this, you fail. No, it's not like that. Right? We'll see this later on. Glucose, right? Glucose is the most likely. There's a couple of other things that it could be, but glucose is probably the most likely. So now what this basically means, and notice it's in position 4, it's in that lower corner. And what this is basically saying is how many atoms of carbon are in one molecule of glucose? 6. How many atoms of hydrogen are in one molecule of glucose? Yeah, how many atoms of oxygen are in one molecule of glucose? So this is telling you how many atoms of each of these is in this one molecule. So this is one molecule of glucose that has 6 carbons, 12 hydrogens, and 6 oxygens. So those are your 4 positions of information when you are looking at chemical notation. So we already talked about mass. By the way, mass, which is essentially protons plus neutrons. Mass in chemistry has always been a little tricky, right? Because typically speaking, the way we get mass is we take something, we put it on a scale, and then we read off the scale in like grams or milligrams or whatever, right? The problem is, how do you weigh the mass of a proton? Which is so tiny that you can't actually put it on a scale. Well, I mean, the problem is you don't have a way to get to it in order to mass it out. So getting the mass of a subatomic particle has always been tricky. One thing we did was we just kind of use reference levels, right? That's kind of what we do, like relative masses. That's what we do because we can't actually get there and get discrete mass. And so oftentimes what we'll do is we'll use like a reference. And so what we do is we say, okay, let's take a look at one thing that we like. How about a proton, right? That's a good one. It's big. It's important. We like it. Protons and neutrons are roughly the same size, but you didn't know that at this point. So let's go ahead and just say this dude who's working on this, Dalton, we're going to call the size of a proton, whatever that is, 1 Dalton, right? So that's just like you're just arbitrarily making this unit. That's your reference point, the size of a proton. Now then, all the other masses are going to be fractions or relative to the size of a proton. Okay, that's how you kind of do that. In Dalton, and actually in chemistry, we don't really work a lot with subatomic mass in Daltons. If you get into biochemistry and work with proteins, you will use Daltons. But generally speaking, we don't use Daltons a lot. In chemistry, we usually grams per mole. So like in chemistry, we were introduced to the Dalton, but we didn't ever use it. In biochemistry, we used it, right? Because we use it in proteinology. There's also another version of this, which is kind of similar basic idea, called the atomic mass unit. Some of you guys will run into that one. And what that basically is an arbitrary reference point. and we just say, okay, proton. That's our reference point. We're going to call that one atomic mass unit, whatever that means. Now, everything else is going to be related to that, right? So if a neutron is half the size of a proton, then it is 0.5 AMU, right? So we kind of use that as a reference point. Okay. So you run into that one a little bit. So that's our protons and our neutrons. Now we have our electrons, right? So we already talked a little bit about our electrons. It's our negative particles. We've already talked a little bit about their ionic state, right? So when they get unbalanced, when you get either more or less. So if you get more protons than electrons, that is to say you've taken electrons away, then you're going to have a net positive charge. We typically call that ion a cation. So positive ions are cations. They have a positive charge. If you have fewer protons, electrons, that is to say that you have added electrons to it, so you've accumulated negative charge, then that's going to be a negatively charged ion, then we call that an anion. So you do hear the term cation and anion from time to time, but generally speaking in biology, we don't use that a lot. Why? Because rather than saying like cation, anion, it's like, well, what are you talking about, right? So are you talking about a specific person like sodium? Then say sodium, right? It's like, I don't, this is like talking about the ion in the third person, you know? It's like, while the person is there, you know? So it's like, I'm not talking to you or about you in the third person. I'm going to talk to you by name. It's like, I'm not just talking about somebody in this room, you know, whatever. It's like, you're talking about me. So if you're talking about me, use my name, right? So that's kind of what it's like. So in biology, we don't really use these terminologies a whole lot, but you do see them from time to time. So let's go ahead and take a look at another important thing, what's isotopes. So this is a little bit of nuclear chemistry. We're going to clean this one up a little bit, talk a little bit about some of the biological applications of this, and then we're going to start, and we're going to leave the nucleus alone. And we're going to focus on the electrons from here on out after this particular piece. So I want to talk a little bit about isotopes. So an isotope is basically what an isotope is, and we already saw one, right? An isotope is basically where you have a single element that basically differs in the number of neutrons. The example that we fleshed out was carbon, right? So here you had 3 different isotopes, right? 3 different carbons, types of carbon. They're all the same element, but they differed from each other in the number of neutrons. How do you know they didn't differ in the number of protons?
It's carbon, it never differs.
Exactly, right? Because if you differed by the number of protons, you wouldn't be carbon, right? So here's a good example of carbon 12, carbon 13, and carbon 14. So you can see here, in all cases, I've got 6 protons in all of them, right? That basically is definitional because you are carbon. But in carbon 12, you have how many neutrons? 6, not a trick question, by the way. Carbon 13, 7, right? Again, 3rd grade math again, right? And in carbon 14, 3rd grade math with some 1st grade reading skills, because you can see it all, right? See, that means you guys are college ready. In 1st grade and 3rd grade, you guys were college ready. So of course the electrons are what, right? Because we're not dealing with electrons, they all, because it's neutral, are all 6, right? Because you cancel everything out. So let's take a look at this. A couple of things I want to tease out before I get to this last concept here, which is the half-life. What I want to do is I want to explain what's going on here. The first thing I want to draw your attention to, and Bella, if you will, because you got the periodic table out. The atomic mass of carbon is what? How many protons did it have?
Protons is 6.
Neutrons?
Neutrons is also 6.
Okay, so what is 6 plus 6? Excellent. Bella, what is the atomic mass of carbon on the periodic table?
It is 12.01, but that's the average of all of the isotopes.
So it is 12.011. So here's the thing. Take a look at most of those elements on there. Are any of them whole numbers? Some of them are, but most of them?
Most of them are
fractional, right? So they're point something, right? So here's the thing. Mathematically, should this bother you? 6 plus 6 equals 12. So my question to you, where does the 0.011 come from? Does a whole number plus a whole number ever create a non-whole number? It's not mathematically possible. So where does this come from? Bella, you hit the nail on the head, right? So you don't have just carbon-12 in nature. And what you see on the periodic table is not just carbon-12. What you see on the periodic table, remember, is naturally occurring isotopes. So here's what you do. Here's how you get the mass of carbon. You take like a bunch of carbon, put it on a scale, and you read it off. That like naturally occurring carbon. Same thing for all the rest of them. You basically just take a certain amount, like a mole of carbon, and you weigh it. That's what you do. And you're going to come up with 12.011. Of course, being a studious scientist, you make the connection, wait a minute, this shouldn't be possible, right? Because last time I checked, you can't have a fraction of a neutron or a fraction of a proton. It's kind of like the statistics where it says the average American family has 2.5 kids. Oh, great, that's interesting. So which kid did you cut in half? Right? So you know that's not possible, right? So the same thing is true here. It's not possible. If you take a look at the periodic table, it's not possible like many, 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 many times over. It's not just a carbon thing, right? There are lots of fractional numbers out there. None of them, most of them, are not whole numbers. So the question is, where does these non-whole components come from? Where does the 0.011 come from? Well, it comes from the fact that your natural source of carbon, any source of carbon, what you ate this morning, if you ate, right? What you are actually made of. All that carbon, all that naturally occurring carbon has all 3 isotopes in it. So when you see a natural source of carbon, the most abundant and the most stable is carbon-12. Hence the reason why this number is closer to 12 than not. Carbon-13 is less abundant. Carbon-14 is less abundant. So in all natural sources of carbon, there's going to be a certain percentage of these naturally occurring isotopes. It's going to be a small percentage, but it's going to be a stable percentage of all of these occurring isotopes in your carbon sample. Okay. Now, how do you know that this is a fairly small percentage of natural carbon? Well, you can kind of see what this number looks like. 0.011 is a pretty tiny number, yes? That means that your isotopes are really not that heavy. There is arsenic. I believe it's got 0.92 after it, I believe, or something like that.
Arsenic is, yeah, 0.92.
And then gold is like 0.97, or is that lead that I was looking at? AU. So gold is 0.97, right? So whatever it is, blah, 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 0.97, right? So because it's close to the next number, that means that those isotopes are heavy, right? So the heavier it is, the higher that point goes. So something that's like 0.9 means that those lesser abundant isotopes are maybe less abundant, but they're heavy, right? Or they're more abundant than the isotopes of carbon. So like when you take a look at gold, it's not just the most abundant gold, it's got like, oh, wow, there's actually quite a bit of these other isotopes in there, right? That's what that's like is when you're weighing that on a scale, it's like those heavier isotopes are like putting the thumb on the scale, making it slightly heavier. If you have a lot of those heavy isotopes, you're pressing down on the scale a lot. That gets you up into that 0.8, 0.9 range. If your isotopes are less abundant, the smaller percentage of the overall, it's just gentle, just a little gentle pressure of the thumb. And that gets you a little closer to kind of more like 0.1, 0.011, okay? But that basically tells us that there's not just one type of an element. There are all these isotopes. Now, here's the thing. When you're looking at isotopes and you're looking at the number of neutrons and protons, there is a sense of stability. So if you are carbon-12 this is the most stable element, which is the reason why it's the most abundant. Now, carbon-13 is less stable, and carbon-14 is the least stable. So this one would be frowny face, smiley face, straight face. All right, that's if you like the emoji version of science communication, right? So is that a question going up? Go ahead. Yeah, 8. Yes. So at this point, it's unhappy enough to where it wants to do something different, and that's kind of, so I'm kind of moving toward the idea, the underpinnings, the physics, if you will, of a process called radiocarbon dating. Some of you may have heard about that. Whenever we discover an ice mummy and we figure out this guy lived 3,000 years ago, how do we know that? It's usually because we carbon dated him. Okay, the Shroud of Turin, for instance, we say like, oh, well, this is a 1st century piece of textile or something like that, or whatever. How do we know that? Because we carbon dated it. Okay, so it kind of gives us some, and we're going to talk about that process, and that's going to lead us back to the half-life discussion on the previous slide. But I wanted to sort of lay out the isotope situation and this sort of the misery index, if you will, of a nucleus. Now, I'm glad you mentioned that, right? Because that's a really good question, is how many neutrons is too many neutrons? Right, well, that depends, right? So it depends on who you are. So different atoms will have a different tolerance for instability, okay? Now, the way this works when you're unstable and an unstable nucleus, think about this for a second. It's kind of like you grocery shopping and you don't have any bags and you're not interested in buying any bags. So what happens? You basically end up taking your entire shopping cart home of stuff, right, randomly packed into your car, but really no significant way of carrying it, right? So here you are now, you've got your car full of stuff and you got to figure out how to carry all this. So you're going to grab some stuff here and some stuff here, start loading up your arms, right? And then there's more to go. So at first you got an armful and you're okay, right? Yeah, I'm full, but guess what? Let's keep adding on to you. So now you got a milk jug on one pinky, on either pinky, testing out the strength of your pinkies. And you got 2 more milk jugs on the ring fingers. So you're going to test out those less dominant fingers, right? And then you got a bunch of stuff here, right? You're kind of like, you got stuff piled up. You got stuff piled up on that. You know, you got things in your teeth, right? They're kind of like this. And guess what? We're going to keep going, keep piling up, right? Because you want to get it all. I mean, this is one trip. You got to go upstairs. You're not doing this twice, right? So this is it. Not only that, but then what do? You're getting really unstable, aren't you? Oh, it gets worse, because then you try to say, okay, wait a minute, I can do this. I'm going to do the tabletop walk. Okay, now I can lay stuff on my tabletop, right? Oh yeah, but you have a big mountain of stuff, but now I'm going to put the eggs on the top. And you got milk jugs in your hands and God knows what else here. And what are you doing? You're like, how happy are you right now? As you go up the stairs. 1, 2, I mean, you're like, you're saying, inventing words that would make sailors blush, right? You are what? Unstable, aren't you? What do you want to do? Lose it, right? Because if you lose some of the items, then you come back to a more stable load and you feel more comfortable, right? Same thing is true for a nucleus. When you get too much stuff in your nucleus, you become unstable. You got to offload some of that stuff so that you can get down to a more stable size. Christopher. Yeah, and that's exactly where we're going, right? Because let's say this guy right here, he's unhappy, right? He wants to do something. He's not going to live as carbon-14. So you need to work on your nucleus. What are you going to get rid of? Yeah, you don't want to mess with the protons, right? Because that would change you into something else. And so basically what carbon-14 will do is it'll kick out a neutron. But guess what? It doesn't actually kick it out. It does something really cool and interesting. It actually converts that neutron to what? A proton. And it hangs on to it. Think about this for a second. If I convert one of those neutrons to a proton, how many protons do I have now? Right, so I have 7 protons, right? 7 neutrons. Is my mass still the same? Yeah. So what do I become? I become something with 7 protons, which is what? Nitrogen. And what's the mass of nitrogen?
14.
And what's my mass? So this cute little trick that I just did here actually converted me into nitrogen. It's almost like you are really unhappy as an overloaded carbon. You're really struggling inside your skin because you are like a carbon, but in your brain, you're wired like a nitrogen. All you need to do is convert one of those neutrons to a proton, and now you look like a perfectly functional nitrogen. 7 protons, 7 neutrons, a mass of 14. And you're more stable. Remember, I said the one time when you're willing to change your identity is if you go to a more stable state. And that's what's happening here. The electrons don't change. Yeah, I mean, obviously, well, you would have to pick up an electron, right? Because you have an extra proton. So you'll probably ionic there for a little while until you actually pick up an extra electron. So. If you have too few, it's a little bit different, right? Because you're fine, you're not unstable. You may not be normal, but you're not unstable. So it's not quite the same pressure. It's not quite the same pressure if you have too few, right? So when this happens, this process happens, you release energy, and that energy is radioactivity. And so what I want to do is, because we are about our witching hour, and you might have to remind me, because I won't remember this, because I've already had this talk with the Monday, Wednesday, Friday people, and the Monday, Wednesday people, I think we've almost had the talk, so I won't remember probably. Did we already talk about this or not? Is we want to talk about carbon dating. Actually, I'll write it down here. Talk about carbon dating. That's where I want to pick up. Okay. And that'll lead us back to this slide here and fold into half-life, and then we'll be able to move on from there. Okay. That makes sense?